So in the lab, we're going to look at how much heat the building loses so we can make some determinations about some choices of windows that we're going to make. So first of all, we need to understand this basic idea of how we measure heat loss in a building. It's really quite simple. Um, Heat loss is equal to a value we call Q, which is BTUs per hour, British thermal units per hour, the amount of water, 1 pound of water raised 1 degree Fahrenheit. So it's an amount of energy per hour. And we find that total Q value by using the resistance, but in this case, the U value, 1 over R, times A, the area of the wall surface or roof surface that we might be calculating, times the temperature differential between the inside and the outside of the building for the hour that we're measuring, because this is in BTUs per hour. So we kind of expand on that calculation um, a little more, but it's important to understand really why are we calculating this heat loss on a building? And we do that for a number of reasons. One primarily is to make sure that we comply with code. What the building codes require us today to have certain performative features to our building to save energy. Roofs have minimum R values, windows have minimum U values to them, and we need to make sure that we comply with code. But remember, codes are the minimum standards. We may also be interested in exceeding that code for either LEEDs compliance or other reasons of saving energy and just good environmental stewardship. So we need to know what our R values and U values are to make sure that we are meeting code, and in many cases, if we desire, exceeding code. And then to determine how that design affects heating and cooling load. And most importantly here, it can just be the sizing of the heating and ventilation system. How large a heater we need because of the maximum amount of heat loss through the building. Um, and then these all keep circling back on each other. We change the size of the R value in a wall. We look at the overall amount of heat that is required for it, the energy cost that goes along with it, and then we can modify that theoretically, and then look at the overall building performance again. So we need to know our R and U values because we need to know how our buildings perform, and we need to know how we're going to change them to optimize the performance. So this idea of the heat loss calculation is really expanded out to this idea of degree days. So I want to introduce this concept that when we look at heat loss for a day, we calculate the amount of time that the temperature on the exterior of the building in the environment is below a certain given temperature. In this case, it's typically 65 degrees. So every hour of the day, if it's, let's say, for example, for the whole day, it was 64 degrees out. On the inside, we wanted it to be 65 degrees out. The difference is 1 degree every hour times 24 hours. We get 24 degree days. So, but we have that automatically calculated for us in some useful websites that deliver, or excuse me, the meteorological data is stored for us, and it can be easily retrieved and placed onto spreadsheets. So in this case, I have the data coming off of a website. I'll click to this right away to show you that it's a live site. You can pick the station, whether you're talking about wanting to analyze something for heating or for cooling, whether you want to use metric or US standards, Fahrenheit, for our temperature measurement, and then how we want our data to come back. We can get it daily, weekly, monthly. In our case, we're going to work on it as monthly data, and it's going to generate those days once we've selected that. So if we go back here, you can see on this chart, I've selected the Wellsville station, and I've asked for heating degree days in Fahrenheit and monthly data. And what it will provide me with is a spreadsheet that is on the left here, which is the heating degree days for the associated month. And we can then use this in other calculations to get the total heat loss for the building. So we have this idea of heating degree days and cooling degree days. Important thing here is that when we have temperatures on the exterior above what we want the interior temperature to be, it is a cooling degree day. And then this, once again, this is the same formula that was presented back here of this idea of U times A times 24 times degree days. So I'm showing you the same formula, but I'm giving it to you in another visual form. So we have the area times the U value, but in this case, it's been simplified down to, instead of using the U value, we have 1 over R times the area. It's the R value is now just in the denominator. So it's automatically the U value times 24 hours per day times the heating degree days for the season, this says, but we could easily say for the day or for the week, or in our case, for the month. And we want to use that data that we pulled off of the spreadsheet. And then just to simplify this calculation by removing the unit designation, the heat loss is equal to the area of the surface we're measuring, whether it be a wall or window, divided by its R value, times 24, times the heating degree day totals that we'll get off the charts. And just another reiteration of that. And this is just a link to a wiki page that talks about heating and cooling degree days in case you're interested in looking at this in more depth. I want to, before we leave this idea of thinking about heat loss, I don't want you to see the whole ball of our design criteria based on just R values. We have, once again, this complete energy picture, the idea of what comes in through the sun, what modifications we make to control the sun entering the building, our natural ventilation, the kind of surfaces, like we talked about emissivity or reflectivity of roof surfaces. So all of these things work together. Thermal mass for flooring to absorb heat, deciduous plants that can shade in the summer and allow sunlight in the winter. All of these things work together as advanced architectural designers that you want to be to create the most energy efficient environments that we can create for our clients. And so once again, that idea of the complete energy picture, these are some nice graphics that kind of remind you about the things to think about. One of them is, in this case, the wind rows. This is the idea of prevailing winds. Once again, another linked resource. So when we draw these sun paths and we draw these arrows on our site plans to indicate which way the wind is blowing, we can go and find actual records, digital data of where the wind blows the strongest from what direction for any given site. So once again, if I was to click on this, it'll take you out to a site that will allow you to get data for any location that you might be basing or working on your project at. So once again, the idea is that Revit already generates, or BIM modelers already generate a lot of this site information with a solar heliostat. We can apply the windrows in three-dimensional models. And then in this case, we generate these really descriptive ideas about why we site a building the way it is, why we plant vegetation around it, how we are oriented for the sun, how we were oriented for natural ventilation. And we might become, once again, to step back a little further, we might be always thinking about heating and heating systems, but much of our climate is predominantly cooled or mixed. So we have almost equal heating and cooling seasons. Most of us are probably familiar with our very cold winters and relatively mild summers. So we think of our built environment as mostly being heated, but for a majority of the country, that is in fact not the case. So just keep that perspective in mind. Just another restatement of what we've gone through already. A reiteration of this idea that U values are usually used to rate doors and windows. R values are typically applied to specific materials and the builds up of things like wall systems. And that's, I think, a good preparation for moving into what will be our lab component of this project to look at some heat loss, do some heat loss calculations on a little mock-up building that we make.